Okay, recording is rolling. It is Tuesday, January 10th. So yesterday, you guys did a pendulum lab. So we're going to just wrap up that day. There's a little bit more we got to do. And then I got a bunch of demos for you guys. Oscillation, waves, a few pages of notes for you guys. I think tomorrow I want to do another lab with you guys. It's on the paper in front of you right now. So if you guys had this page out from yesterday, pendulum lab, we just got to knock out these last two graphs and get the conclusion. We're about to do that. The opposite side of the paper is another type of oscillation. It's got a block on a spring. It's going to bounce up and down. So that'll be tomorrow's adventure, because that's the plan right now. Thursday, I think I want to do puzzles with you guys, and then we'll see where we are from there. What we're going to do with Friday. Monday, of course, is Martin Luther King Day. Oh, and don't worry about 80 class. It's not for you guys, right? So, all right. So that's our plan. Okay. So, oh yeah.
So our new classes, do they start on Thursday?
Okay. Let me check that. All right, recording is resumed. All right. So far, you guys have time periods a function of mass of the pendulum bob. You guys know it's a flat graph. You guys did that one yesterday, right? Which means no relationship. It doesn't matter what the mass of the bob is, right? The time period is the same, right? Same thing with the starting angle. Whatever angle you pull the pendulum back to, actually also did not affect the time period, right? Okay. Let me pause this thing. Okay, recordings resume. Right, so you pull back to whatever angle, and it's the same time period regardless. Right, and then this is the last graph we did yesterday was time period versus length. Actually, let's get this one from scratch. Anybody got a numbers they want to volunteer for length of pendulum? Length of pendulum? Sure. Go steal one of your lab papers. Got good numbers? Yeah, thank you. I'll bring this back to you. All right, so let's see, Dylan's sharing some numbers. Got lengths that, no, these are all in centimeters. 53, 47, 34, 33, 27. Oh, whoops, those were lengths. Oops. Well, okay, we have weird colors, whatever. Okay. All right, and then the corresponding time periods. Okay. Got 1.25 seconds there, 1.11. 1.12, 0.98. Oh, and this top one is 1.61. Okay. All right. We'll go with that. Thank you. All right. So I think you guys have that graph. That was the last one you got yesterday, right? A little bit different numbers, but same idea, right? Right. And then the bell rang at that point. Okay. Now, to finish this off, we got to figure out, since we know mass and starting angle don't matter, but length does, right? The longer the pendulum, the more time it takes to swing back and forth. Well, what kind of relationship is that exactly? Like, is that a direct relationship? Like, at a glance, it looks like it might be, but I don't know. If you draw a straight line between these, you guys see there would be like a huge y-intercept here, which is maybe a hint that this is something that you've seen over and over and over in past labs. This might actually be possibly a square root relationship. Do you guys think? Maybe like a root relationship? You think it like hooks down? Right, you guys think? Right. So suppose you suspect a square root relationship. Let me bring this over here. A little bit of algebra with you guys. Okay. Suppose you think time period is proportional to the square root of the length. But maybe that's a question, right? Okay. Is time period proportional to the square root of the length? Okay. Proportional to is kind of like an equal sign, but I'm leaving off part of the equation because there might be more to it. Okay. Just these two variables. Now, if that's true, if you made a new graph, this is what we're about to do. Okay. Time period in seconds as a function of not the length in meters or centimeters. No. Okay. The square root of the length. It's gonna be like square root of centimeters. Okay. Then the points should line up pretty well into a straight line. And that itself would be a direct relationship. And if that's true, if that happens, then we can confirm that there is actually truly a square root relationship between time and length. Okay. Alternatively, I'm actually going to have you guys do two graphs because I want to see this works either way. Okay. You could do a little bit of algebra manipulation first. You could say, what if you square both sides? Could this be time period squared proportional to just plain length. Okay. That should work out the same way. So if you have time period squared, now this would be in square seconds as a function of length and centimeters. Okay. Should also line up in a straight line. Okay. Now, these two graphs would have different slopes with different units, like totally different concepts, but they would both be straight. Okay. And they would also both be have something to do with the gravity field of the planet. Like if you took a pendulum up to the moon, do you think the pendulum on the moon would swing back and forth really slow? Yeah, because really weak gravity really slow, it would swing back and forth, right? That has something to do with the slope, and it's not exactly equal to the slope, but get to that a little bit later today. All right, so switch back over here. Now, I have Excel pre-programmed to make both of those graphs for you guys. Right, these are the last two you're going to copy. So you guys see on your lab page on the right side are these two spaces for graphs. Okay. All right, so we're about to make both of those right now. All right, well, one at a time. Okay, here we go. Let's start with this one. Time period squared versus length. Look at that. That's pretty good, I think. If I right click on one of these points, add trend line, straight line. Yeah, look at that. A linear relationship. That is pretty good. I think we go with that. So go ahead and draw that as one of those two graphs on the right. Okay. So guide you guys along here while you guys are copying this. The vertical axis, label that as time squared, and the unit would be square seconds, like seconds squared. And then scale that from 0 to 3. 0, 1, 2, 3. Exactly like you guys see on the screen. Yesterday, we did everything by hand on the projection. Today, you guys are copying from the screen. That's the same idea, right? And then the horizontal axis, label that length in centimeters and scale that 0, 20, 40, 60, just like you see on the screen. Okay. Put the dots about where they go. Draw a straight line, line of best fit, which shows a direct relationship. Okay. Oh, yeah. Gonna repeat those directions while you guys are copying that down. Just make sure you know exactly what's going on. The vertical axis is time period squared. That's capital T squared. And the unit is square seconds. I also drew this up on that paper before I switched over here. So time period squared and square seconds. And scale that 0, 1, 2, 3. The horizontal axis is the length of the pendulum in centimeters. Scale that 0, 20, 40, 60. Put the dots about where they go, and they pretty well line up in a straight line. Zip a line through that, line of best fit, and zip. You showed a direct relationship between the square of the time period and the length of the pendulum. That's everybody's got that graph? We got that one? All right. So now we're going to switch over and do the very last graph, which is just a little bit different perspective on the same thing. All right, you guys ready for the last one? Right, it's going to be a similar looking thing. Right? So what if instead you have time period versus the square root of the length? Look like that. Right, so also lines up in a straight line. So add trend line, line of best fit. Okay. Let me scroll back and forth between these two real fast so you guys can just contrast these. Right. So this one, right, the dots look about like that. Here, there looks like their dots are kind of smushed up to the right a little bit more, but it's still a direct relationship. Right. So put the time period in seconds on the vertical axis. Scale that like 0, 1, 2. I think that will contain the data, right? 0, 1, 2 on the vertical axis. And then the square root of the length is on the horizontal axis. And that's in square root of centimeters. And scale that, what is it? 0, 2, 4, 6, 8. Contain all the data that way. Put the dots about where they go, line of best fit, zoop, direct relationship. Say it again, make sure you guys are getting this. So label the vertical axis capital T time period, and the unit for that is seconds. So capital T in seconds. S per seconds. And scale that 0, 1, 2. The horizontal axis is the square root of the length. So that's square root of L, square root of the length. And the unit for that would be square root of centimeters. And scale that 0, 2, 4, 6, 8, just like you see on the computer screen. Put the dots about where they go. They pretty well line up in a straight line. Zoop, line of best fit, direct relationship. All right, you guys got that graph too? Okay, so you guys got both those graphs. Of course, you got the ones from yesterday. So that means you have all the graphs. So everybody has all the graphs. Okay. All right. So switch back over here. Okay. Because the very last part of this is this box at the end. Because the whole goal was to figure out, well, what is the equation that governs the motion of the pendulum? Like if we try to account for all these variables, right? Bring them all together. Okay. Of course, these two variables turns out didn't matter. Okay, so it's just between these two, right? And the answer is actually the answer is this right here. Time period is proportional to the square root of length. So see down in this box says time period is proportional to. Used to is a different proportional symbol. It's just easier to make the little squiggle though. Okay. So the answer is the square root of the length. So did you guys write that right there? So the answer is time period is proportional to the square root of the length. Okay, that's the answer to lab. So did everybody write that in that bottom box? Okay, guys with that? Okay. Now, what does that mean? This proportional to is kind of like an equal sign, but I'm saying I'm leaving off part of the equation. Like there might be a little bit more to it. It's this thing. There might be a little bit more to the equation, maybe something to do with gravity field, maybe. Oh yeah, it's better. Okay, okay, we got it. All right, how about this? Suppose I have two pendulums that are different lengths and they're both swinging next to each other. Okay. And one pendulum has 4 times the length of the other. It's like one's 1 meter and the other's 4 meters long. Guys, what would the ratio of the time periods be? 4 times the length. Square root 2. Yeah, twice the time period. Right. So if one took like 2 seconds to swing back and forth, the other would take either 1 second or 4 seconds, depending on which way you're going. Okay. What about this? What if you have two pendulums and one pendulum is 9 times the length of the other? What's the ratio of the time periods? Like 3 to 1? Okay, it's the square root of 9 is like 3. Okay, you guys get that? All right. Okay, so you guys good so far? Okay, so you should have this whole side finished. Now, the opposite side of the same paper is a different lab. I want to save this lab for tomorrow, I think. So we're gonna go some analysis on some springs, some boing, oscillate up and down. Okay, so that should be tomorrow's adventure. So hang on to that paper for tomorrow. All right, recordings resumed. All right, so I just gave you guys this packet right here. So let's kind of do this real fast. It's something put together over the break. First page of slides is related to oscillating motion. I have some video demos for you guys lined up today. Okay. Next couple of pages are all related to waves. So we got harmonic motion, like oscillating motion. We got some to do with waves. And on the back, I got space for a lab that I think I'm going to do with you guys next week. It's going to involve like pipes and tuning forks. And so we'll definitely hold on for notes and also a lab next week. All right. So let's dig into these. Very first slide. So the classic pendulum. Here it is blown up. Oh, these are all, of course, the posters hanging in the room. Okay. Oh, hey, look at that. This is what you guys just did yesterday, and we just wrapped up this morning today. So, if you have a pendulum swinging back and forth, what's equation that relates all these variables? Okay. Now we're assuming the string itself has negligible mass, so that all the mass is in the bob. We're assuming this angle isn't too big, so maybe like 20 degrees or less, or somewhere there. Okay. And here's the full equation. Time period, time to swing back and forth, is equal to 2 pi times the square root of the length of the pendulum divided by the gravity field. Okay. And what do you guys figure out? Well, as much as we were able to put together was this bit right here. Remember I was saying, you guys figured out time period is proportional to the square root of the length. And proportional to means there's probably more to the equation. Boom, there it is. That's the full equation. Remember I said gravity field has something to do with this. Okay. Okay, so that's where I put in Earth gravity versus moon gravity. I can tell you exactly what the time period should be for a pendulum of some given length. Is that helping right there? Okay. Now here's a larger picture version of this. I don't think this really shows up in your guys' textbook, but I'm going to throw this anyway. What if you have a pendulum swinging that all the mass isn't in the bob? Like if you have a hanger swinging on a doorknob. Okay. Well, here's a more general version of this. But this does, one thing I sort of want you guys to see is that this does simplify to this. if you assume that the mass is a point mass, because capital I is rotational inertia. Okay? You guys remember for a point mass, rotational inertia is mr squared, right? In this case, r is the length, so it'd be ml squared. One of these l's would cancel, and it just it just simplifies to this. Okay? Okay, so here's more general version. You might never see this again though, but it's there. Okay. All right. There's another kind of oscillating motion. You guys might see, and I'm going to do this probably tomorrow with you guys as lab. What if you put a mass on the end of a spring and pull it back and let it go and wow, 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 like oscillates back and forth? Okay. Oh, look at that. That time period formula has the same structure as the pendulum one. Here's the two side by side. Look at that. Right? Time period is equal to the square root of something, right? So some ratio. Right? And even the ratio, there's some analogies here, because length of a pendulum or the mass that you tag on the into the spring, that's something you could change out pretty easily. Okay? And the denominator down here is some constant that's kind of harder to change, kind of hard to change the gravity field. It's kind of hard to change the stiffness of the spring. Right? Look at that, right? Got that. Then so this will be tomorrow's lab, be something more like that. Now, something I want you guys to see about oscillation, this is going to relate to these graphs, is like a segue into that, is suppose I have a couple of oscillating springs, like one's vertical, and one that's horizontal. Maybe the horizontal one, I should have drawn like a surface here, like a frictionless surface with negligible friction, right? Something like that. So it's just oscillating horizontally. Okay. Now, both of those, this equation still applies. It doesn't matter. This could be vertical or horizontal. It doesn't matter. This still applies. Okay. One thing that's interesting too is I suppose I have a car driving around at constant speed. Notice I'm not saying constant velocity because he's constantly changing direction, but constant speed, speedometer is staying the same, right? Okay. What's interesting is that the his x coordinate, his y coordinate would exactly match each of these bobs. Right? So x coordinate for this guy and y coordinate for this guy. Right? They would always be aligned. Okay? And what that means is that the location motion of each of these could be defined by a sine or a cosine curve. Right? This is what sine and cosine are, right? Doesn't cosine tell you how far right or left you are in the circle, and sine tell you how far up or down you are in the circle, right? So that exactly leads to this right here, these oscillatory graphs, right? Where they're watching the side-to-side motion of this pendulum, as long as the angle is small for the pendulum, right? Or the up and down motion of this mouse on the spring. Right? So we got displacement versus time, velocity versus time, acceleration versus time. Hey, those are the three classic sets of axes for kinematic motion, right? And so suppose you have like a sine curve to represent the position versus time, right? Sine curve. Right? Well, if that's true, then it turns out that the speed versus time is related to that. It's rate change of position, right? Ends up being a cosine relationship, and the rate change of cosine ends up being a negative sign, right? And then you can, there's actually one more rate change you can do to complete a four-part pattern, which is the rate change of negative sign is negative cosine, and the rate change of negative cosine just flips back to a sine relationship. So then it cycles over again. So you be like 4 parts. The rate change of acceleration. Does anybody remember what rate change of acceleration is? I may mention it like once ever. Right? It's called jerk. Right? So anyway, right, so got like these 4 parts. Let's see, show of hands. How many guys are taking calculus? Okay, right. So this probably looks familiar, doesn't it? Right. Rate change of sine is cosine, rate change cosine is negative sine, and so on. Right. The 4-part pattern. Right. So some other things here. Capital A stands for amplitude. That's like this. Here's your amplitude right here, which I think we're about to do pretty soon. Right? Capital A is the amplitude. Okay. And then what's the deal with this omega? All right. So we fill in some details here. Omega is called angular frequency. Okay. Which is 2 pi times just regular frequency. Okay. But what is regular frequency? Regular frequency is the reciprocal of the time period. Right. So like 1 over seconds. By the way, this goes back and forth. So I could say time period is the reciprocal of frequency. Either way, right? Okay. So frequency I'm going to measure in, well, here, let's start with time period. Okay. This one's more intuitive. It's some number of seconds. Some number of seconds for the time period. Okay. But the frequency is, well, 1 over that. right, which is called hertz. So if you ever hear hertz, yeah, so it's like cycles per second, right? Cycles per second, right? And then if you multiply that frequency by 2 pi, you get angular frequency, which fits very nicely in these like sine and cosine type graphs, right? Oh, something by the way, you guys see about this angular frequency, you'll notice too if you're from a taking calculus, but oh yeah, if you're in calculus, what is this called? Why is this omega squared? That's called the what rule? The chain rule. You guys remember chain rule? Yeah. All right, that should look familiar to you, right? All right. Let me do some demo stuff with you guys here. Yeah. Okay. Still. You guys hear 1 beat per second, like 1 cycle per second? Okay, so could I call that 1 hertz, right? 1 cycle per second is like 1 hertz. And wouldn't the time between each beat also be 1 second? Okay, so 1/1 is 1. Okay. Hey, let's speed that up. Ooh. You guys hear 2 beats per second? Could you call that 2 hertz? And what would the time period be between each beat? Half a second, right? 1/2 is like half a second. You see our time period and frequency are reciprocals of each other. Right, is that 4 beats per second? Is that called 4 hertz? What's the time period between each beat? A quarter of a second, right? 1/4. All right, let's do one more. You guys hear 8 beats per second, right? So you're gonna call that 8 hertz. So frequency is 8 hertz. What's the time period between each beat? Yeah, 1/8 of a second. There you go. Okay, just like that. Okay. Hey, what if I kept increasing in frequency? Like it's at some point you think your brain would lose track of the beats and just hear like a hum, like right? And if I kept doing it, would that sound like a musical note, right? You guys think that every single musical note has a frequency associated with it, right? Yeah. But musicians in here now. What if I did 440 beats per second? Call it 440 hertz. Okay. What note is that? Defined as an A note, right? It's modern instruments usually. It's one of the musical notes there, right? Right, so right. Cool stuff to know there. All right, oscillation linearized. All right, now this is more of an AP focus type thing, but we kind of did this at the beginning of class today, right? So you guys graph time period squared versus length. You remember it all came out in a straight line. Okay, so you guys just did this, sort of, right? And I said the slope had something to do with gravity, but it wasn't gravity itself. Oh, what does it mean this? So if you take this formula, you can manipulate a little bit and you can linearize it and it'll look like this, right? So you can actually get the gravity field from your pendulum data, and it should be like 9.8 meters per second squared, right? Got this. And then when we put tomorrow, when we put the mass on the spring and it's bobbing up and down, very similar type story. Okay? So you can linearize this. Okay? Yeah, it's more of an AP focus type thing, though. Take AP physics, this type stuff. All right, let's switch over and look at waves. Right, so what are some basic properties of waves? Got this classic transverse wave going on here. And so how high it bounces up to, well, from this little nodal point, it's called amplitude, capitalized amplitude. I wonder what is the smallest portion that could copy paste next to itself and it would still complete the full wave, right? That's called one wave length. And one way to measure one wave length, represented by Greek letter lambda, is crest to crest, right? You don't have to measure crest to crest though. You could do like one full S shape. I like to do that too. Right? You guys see like one full S shape there? That's like the smallest like fundamental unit you could copy paste next to itself. Right? That's good. Right? Now, if you have what's called a scanning wave, where it looks like it's just like bouncing up and down in place, these might be what are called nodes, right? Where they don't actually move at all. Right? And then these would be your antinodes that just like with the full height of the wave. Got a lot of demos I'm trying to switch in here, so I'm switch my screen over, show you guys that. Okay, where's share screen? Okay. Well, okay, here's an animation of this anyway. So standing waves. Right. So you bounce this up and down. Oh, look at that. Right. You guys see where you're holding it at the ends? Right, those points don't actually move. So there'll be nodes at the ends, right? This is an anti-node in the middle. Right. We could shake this a little bit differently. Ooh, look at that. Right. You guys see a node right in the middle? If you go up and touch it in the middle, it doesn't actually affect the wave, right? Okay. These are standing waves. Not all transverse waves are standing waves, but you can create standing waves. Ooh, look at that. Right. Hey, how about this? What if we're counting the number of wavelengths? We rewind a little bit. Okay. How many wavelengths do you guys see right there? How many wavelengths? Is that exactly one? I think that's one, right? Isn't that one full S shape? Okay. What about here, go to the end here. How many wavelengths is that? Two. Ah, yeah. You see one, two full S shapes, right? Oh, wait, if that's true, if that's two wavelengths, what is this right here? Is that half a wavelength? Yeah, I think that's half a wavelength right there. It's only half the story. Okay. And what about that? Is that 1.5? Right. Okay, so standing waves on a string can looks like the wavelengths can increase by increments of half a wavelength at a time, right? Okay, and yeah, back to two wavelengths right there. Wait a minute, I got a different version of this too. Is it this one? No.
Keep it something like vibration.
Okay,
This is
oscillator.
the frequency here, so it vibrate. So let's
look at
start
that.
the string from the woofer. Let's and of course you can
Oh,
see
look at that. It's bounced up and down.
it's the same behavior
Look
as
at
I keep going up.
Yes, 3 wavelengths right there. 1, 2, 3 wavelengths. Okay, so that's fine. All right, how about these formulas down here at the bottom? All right, well, I went over this one with you guys. Frequency is 1 over the time period, or time period is 1 over the frequency. They're just reciprocals of each other. Okay. And this one right here, super important wave formula. So you guys know V is like velocity, like speed. So what's the speed of wave propagation? Lambda, well, there's your wavelength in say meters, and frequency could be like hertz, 1 over seconds. Okay. Hey, meters times 1 over seconds is that like meters per second? Oh, that describes the wave speed. Okay. Whereas I was back in college working with other engineering students, and I said, I forget exactly how this equation fits together. It's like, oh, well, think about how the units work, right? Meters per second is meters per second. Okay. So there you go. All right. Now there's two main categories of waves, two wave types. Some textbooks have like a third one or something. I just care about these two, right? So transverse versus longitudinal. So transverse is if the individual particles are, say, bouncing up and down, but the energy propagation is left to right. So those are perpendicular to each other. The particle motion versus the energy propagation would be perpendicular. But in a longitudinal wave, everything's in the same direction. So like everything's left to right. Pressure waves are longitudinal. And I've tried to draw it here. Suppose each of these dots is like an air molecule, right? Hey, how are you guys hearing me right now with a sound wave, right? Does sound travel in a vacuum? No, sound needs some kind of medium. No, it doesn't have to be air. Sound also travels through like water or solids also, but it needs some kind of medium, right? Versus light, you guys know, can travel through the vacuum of space, but sound needs a medium, right? It's like a pressure wave. Here, let's do it. We're doing. Demo time. Let's go. Here's. I'll do an animation version of this. Transverse longitudinal. Boom, boom. Just like that. Okay, you guys got that? Do that one more time. Transverse longitudinal. All right. All right, interference. So actually, I think the best way to explain this page is more demos too. So we'll switch over and let's look at constructive interference. You guys see those two pulses are passing. You can just add their amplitudes together. It's like 10 centimeters and 10 centimeters makes 20 centimeters. Oh, look at that. They cross right through each other too. Ooh, that's really cool. Hey, how about destructive interference? Like what if one pulse is positive and one pulse is negative? Let me pause right here. Right. So you guys see those two pulses, they're about to cross over each other. It's all slow motion. Okay. What do you think is going to happen? Are they going to kind of cancel out? Because they're right? Are they going to still pass through each other? Just like the last video, they passed through each other. Are they still going to pass through each other? Let's see. Look at that. all that happened. They did, right? So they canceled out while they were crossing, but then they went in and just passed through each other. Right? One more thing you'll see too, I want to point out is one of these actually reflects off the left, right? So, see this again. Zoom. Now watch this guy as he reflects. Bam! See how it reflects and then goes like upside down? Ooh, that's kind of cool too, isn't it? Right there. All right, so constructive, destructive interference. Cool things you can do with this. Oh, do you guys know noise canceling headphones? You guys ever put on a pair of noise canceling headphones? That's actually this right here. Right. Of course, it's sound waves, which is more like longitudinal rather than transverse, but it's the same principle, right? So there's an active process going on with noise canceling headphones. It takes the ambient sound from the outside world, just inverts it, puts it on top of its stuff, and just destructively interferes it. So it sounds like silence. Interference pattern. So what you guys are looking at here is called a double slit experiment. This is a really famous experiment from way back in the day. There was a question for hundreds of years of what is light fundamentally, because usually things either fundamentally come in terms of like particles or waves. Right? So what is light? Is light fundamentally a particle, fundamentally a wave? The answer, by the way, is both. From back in quantum mechanics. But this is an experiment done that for a long time. Oh, well, light must have these wave-like properties because if you have a wall and put a couple of slits in it and shine some light through, they'll create this interference pattern on the back wall. Anytime you see an interference pattern, that's an indication you might have some kind of waves going on. Okay. Here's a lab I want to do with you guys next week. It's on the back of this packet. So suppose I have a pipe and I dunk it in some water. This light blue is about water. Right? It can raise and lower the pipe in the water so it flows off at one end. Right? Put a tuning fork above it, strike the tuning fork. Bing! Right? Now, as you raise and lower the pipe, at some point it's going to resonate. It's kind of like same thing here. Good. You guys hear that? Right? So there's some place where it'll set up a resonance, like it'll resonate with itself, but only at these certain intervals. Now, something you'll see too is see how I'm trying to show like air molecules here. It's like a high pressure point just above the water, above the close in, and maybe like another high pressure point right here, okay? And then a low pressure point, low pressure point, low pressure point. Is that? Now those are because sound is a longitudinal wave, but also it's really hard to draw a longitudinal wave to like sit here and draw a bunch of dots, make it legible, and know what you're looking at. So it's really common to just whip off a transverse wave to represent a longitudinal wave. So even though these are all drawn as transverse, you guys know they actually represent longitudinal, right? You guys get that? Yeah. Okay. Hey, what if you have a pipe open at both ends? For example, a flute, right? A lot of musical instruments, recorder, but ever play one of those, right? Open at both ends. Certain places will set up standing waves. Okay. Here's standing waves on a string. I played you guys some videos of this. Okay. So there's certain intervals where you can set up these standing waves specifically. Okay. Not all waves are standing, but you can set up standing waves at certain intervals. Oh, what's the physics of instruments? So stringed instruments. Right? If you play any kind of stringed instrument, what's going on there? Okay. So here's the physics formula to tell you. All right, suppose you're tuning an instrument, tuning a guitar, tuning a piano. Same idea. Tuning a cello. Right? Here's the tension in the string. Okay? Here's the linear mass density. Right? Mass per unit length. If you know the mass of the string and the length of the string, linear mass density. Right? Right. Divide those two, take the square root. That'll tell you the speed of the wave on a string, okay? Which is kind of cool, but you really care about the frequency of the note, right? Because every note has an associated frequency, right? So how's that really? Oh, well, I remember this right here. Speed is equal to wavelength times frequency. And in this case, this type string, you guys know that the wavelength is twice the length of the string. We talked about that earlier today. Right? So see how all these formulas are going to speed into each other, right? Now you have a relationship between what's the tension in the string as you're tuning it, okay? And what's the frequency that it produces, right? A little bit more stuff on musical frequency ratios. So, how about this? How many different named notes are there before it cycles back to the next octave? Like if you include all the sharps and all the stuff, right? How many different unique notes are there? Some of you guys know. Were you guys thinking 12, right? Right? So you start at one note, hit every single like semitone all the way up to the octave. There's 12 individual ones. Oh, here, I got a poster over there. You guys see guitar chords? There's 12 different rows there, right? Goes from A all the way down to G sharp down at the bottom. Right, so it's a kind of a cultural thing, sort of. Like if you go to the Middle East, they have like 24 notes. They go to like quarter tones, but it's sort of not. It's kind of a universal thing. Okay. Now, if you go back a few thousand years ago, the way Pythagoras thought about it is he was like banging on different pots and I was going, hey, look, these two pots like harmonize well together. He thought, all right, trying to figure this all out from scratch. Was that there are certain frequency ratios that sounded good together. Okay? So it turns out that if you double the frequency, half the wavelength is another way to think of it. That is going up one octave. And you can do the other way to get like half the frequency. You go down an octave. Remember earlier today, I was telling you guys 440 hertz was an A note, right? Well, if you double that to 880 hertz, or if you half that to 220 hertz, that's just an A note above or an A note below. Right? So an octave above or below. Right, how about some of these other ratios? 3-2 ratio in terms of the frequencies is like a fifth or a perfect fifth. Right, here's like a major third. Now, a couple hundred years ago, a lot of instruments were tuned according to this like Pythagorean tuning, right? There's actually different tuning standards, but the modern tuning is actually not exactly this. It's actually equal temperament, which involves this this exponent formula. It's like a logarithmic type scaling, right? Which is really close to this. It approximates it, and I'll show you guys that that's the case, but it's not exactly. So remember, I told you guys there's 12 individual notes, right? From like A to G sharp, for example. Okay. So N represents the number of half steps you are away from the root note. Right? So I'm going to take a root note, for example, 440 hertz could be, right? Multiply by 2 to the power of something. Okay? So let's say you count up 12 half steps. Guys, what's 12 over 12? 1. What's 2 to the power of 1? 2. Oh, double the frequency. Boom. So that works exactly, right? Works exactly for the octave. Okay. What about the fifth? Okay. Now, the perfect fifth is actually 7 semitones up from the root. So 7 over 12. What's 2 to the power of 7 over 12? Okay. That is 1.498. Ooh, that's extremely close to 1.5, which is almost a 3-to-2 ratio. It's off a tiny, tiny, tiny bit, but almost imperceptible, right? This one's off a little bit more. Here, I'll show you. So the major third's like 4 semitones up. I pop a 4 in here. 1.2599. That's not exactly 1.25, but it's really close, right? And that one your ear might be able to tell the difference. Like, there's a little bit difference. Okay, but all your modern musical instruments are pretty much using equal temperament. Okay. Doppler effect. All right, so I got a demo for you guys while I'm rigging this thing up. You guys ever stand on the sidewalk and a car goes by, something like, you hear some kind of pitch shift going on, pitch shift, right? Now, of course, if you're inside the car, you don't perceive that pitch shift, but outside the car, you do. Okay? So something to do with the motion of the observer and the source. So that's some different frequencies, like a different musical note, right? Okay. All right, so you guys hear this tone? Okay, which is down here. Okay. To get this going in a circle around my head. You guys do hear it's a single solid tone, right? You guys hear a pitch shift? Okay, I'm glad you do. I'll have to take your word for it because I'm at the center of the circle. So to me, it just sounds like a solid tone. Is it rising as it gets closer to you and falling as it goes away? Right? Should be, right? Okay. All right. So it's up for next class. All right. So example of a Doppler shift right there. So has this here, I'll call the car like the source. Say like he's moving like, or maybe the engine or it's like beep beep or hey, maybe it's like an ice cream truck playing a song, right? Sounds super eerie as it passes you. Okay. So the speed of the waves going out to the world does not depend on the speed of the source, right? The speed of the wave is just whatever it is through the medium, right? The speed of sound is whatever it is. It's like about 340 meters per second, right? In all directions. Okay. But the frequency that these wave crests are hitting the observer can change, right? The source is headed towards the observer, for example, right? Be more frequent. Okay. Right, so here, let's start from if the car is parked. If the car is parked, then everybody agrees on the frequency. Like, oh, it's all the same, right? But if somebody's in motion, this guy's in motion, this guy's in motion, the observer, the source, right? Well, get this whole setup. Right? And notice it's a plus or minus because you might have one or both these, the source of the observer, maybe running away, running towards, driving away, driving towards, right? So that's what the plus or minus is about, right? And if you want to navigate this formula, you have to figure out, well, what would make sense? What's going to increase or decrease some frequency, right? Got the speed of sound here, about 340 centimeters per second, depends on the temperature and pressure. Right? Speed of the observer, this guy running back and forth, speed of the source, This guy driving back and forth. Okay. Right. Frequency observed. What's this guy here? Ooh, supersonic. Hey, would it be possible? Could this car be going so fast that it's actually outpacing the various sound waves it's sending out? Is the theory, right? Like a supersonic car, probably. Well, I drew a jet here because it makes more sense for a jet, right? Okay. So if you're traveling faster than the speed of sound, okay. Hey, you guys ever heard of Mach number, like Mach 2, Mach 3? Okay. Well, that just means how fast are you going compared to the speed of sound. If you're going 3 times the speed of sound, that's called Mach 3. Okay. Hey, what if there's an observer down here, like standing about where this letter A is? Okay, the observer. Right. Watch the plane pass. Has the observer heard the plane yet? No. Right. Aren't all these wave press going to hit him at the same time? Like, bam! And he would experience a what? Sonic boom. That's what sonic boom is, right? Sonic boom. And finally, decibels. Now, decibels is a way to measure like, how loud does it sound. Okay. But this is on a log scale, so works a little bit weird, right? So what's going on like at a physics level is that a sound wave might have some associated pressure you can measure in pascals, or another way to do it is intensity in watts per square meter. Right? Now there's 2 different perspectives on what could be like the same idea, 2 different ways to measure those. So here's how you get decibels going through pressure, and here's how you get it through sound. This whole story behind this. There might be a couple of applications for this in this class the next couple of weeks, right? But like right now, as I'm talking to you guys, it's probably pretty close to 60 decibels. What would it mean to go to like 30 decibels? Now 30 decibels, might barely be able to hear. Or what if you doubled it to 120 decibels? Is that double the sound? Well, that would like pretty well like blow your eardrums out, right? If you're going like 120 decibels, because it's like 20 pascals of pressure, like difference, like oscillating back and forth. So I remember this all like on a log scale. Here's the equations that that's attached with. We might solve a couple of those down the line. All right. Well, we got about a minute to the bell, so that worked out pretty good. You guys got any questions, anything today? Oh yeah.
You know like about like how many miles an hour it is to reach the side?
Oh,
It's 1,400 kilometers an hour. So that's probably
yeah. Let's see. I think I can Google that real fast. I should know speed of sound in miles per hour. So 767. So somewhere about there. All right. There we go. Yeah, of course I know the meters per second one myself. But so that is a wrap on today.